Thank you, Tandon sir, for my introduction. Am I audible properly?
Yes, yes.
Yeah. So this is a lecture series of 4 lectures. So if we look at, say, the entire disaster management, so there are many aspects in it. So I'll share my PPT slightly after a few minutes. So there are actually 6 aspects in any disaster management. One is prevention, second is mitigation, third is preparedness, fourth one is response, rehabilitation, and reconstruction. So these are 6 aspects. But when it comes to earthquake disaster management, prevention is not possible. Earthquakes we cannot prevent; they are natural events. So we are left with 5. So 2 before event, that is mitigation and preparedness, and 3 after the event, response, rehabilitation, and reconstruction. So as you all know, the first principle in surveying, that is whole to part. So the topics which I have chosen for this lecture series are in a series like, say, first I would like to discuss about structure, and then next lecture soil, that is geotechnical aspects of tall buildings, and then after that how we are going to index, how we are going to measure the risk of a city. So that is risk indexing. And fourth one is overall management. So how do we do disaster mitigation, earthquake disaster mitigation and management. So these are 4 lectures in one after the other. So let me now share my screen. Attendance of one small correction in my introduction. I am a faculty member at IIIT Hyderabad, not IIT Hyderabad. Please make note of it, all the audience. Yeah. So.
One always forgets the third eye.
Yes, sir.
IITs are more popular and common, and IITs are many people do not know even IIT.
I think you should call it, this is the I cubed T.
No, but the IIT is a standard term now. People know by the name of IIIT.
Yes, I think one should call it triple I.
IIIT. Okay, sir. So let me start.
Yes.
So the topic for today is earthquake safety of RC tall buildings in India, and with special focus on 1893 and 16700 provision, that is tall building code provisions. So I'll be discussing or presenting for around 60 or 60 plus minutes, and after that we'll have some 15 minutes of question and answers. So in the meantime, whatever question is there, you can type in the chat window. So yeah, so this is a glimpse of like some of the tall buildings in the world. So presently, so Burj Khalifa is the tallest one, and many tall building projects are there on the cards. And then some of the good buildings in the country which are already existing, and some are coming up. But there are several projects of tall building under waiting are in the pipeline. Now, what I'm going to discuss today is the outline of my presentation. That is, first I will briefly discuss about the risk, and in detail I will discuss this in the second lecture. And then how the earthquake hazard estimation or assessment of that hazard vis-a-vis tall buildings. So what we are going to talk is what, why, and how this earthquake hazard. Then earthquake behavior of tall buildings. So with I would like to comment, or I would like to give some glimpses of what happened during recent Nepal earthquake, this 2015 Nepal earthquake. And then IS code provisions, especially I'll focus more on 16700 provisions and some provisions from 1893. So time is short for all the provisions, so we can discuss sometime later. And then one experiment we did on like what is the validity of the current empirical expression for natural period. So whatever is given in IS 1893, and then we conducted some experiments on tall buildings, over 80 to 100 tall buildings, and we are proposing one empirical expression for tall building. So let's straight away go into the details. So risk. So risk, earthquake risk. So earthquake risk is composed of three important parameters. So they are hazard, vulnerability, and exposure. These are the three components of earthquake risk. So if we combine them, we get risk. So hazard is not in our hands. When I say earthquake hazard, that we cannot control, but controllable parameters are vulnerability and exposure. It is something like in these days in COVID period, we can say hazard itself. Hazard means virus itself is hazard. Vulnerability is immunity of a person, and exposure is real exposure. So what we need to focus more is on vulnerability, which I'm going to focus today. So risk consists of three things: hazard, vulnerability, and exposure. Hazard is like nature is defining that. Nature is defining that. So according to our IS zonation map, we have 4 seismic zones: zone 2, zone 3, zone 4, and zone 5. And then vulnerability is decided by architects and engineers. And then exposure is municipality. In a way, something like a floor space index and other details come under exposure. Now, hazard. What is hazard? Hazard is the level of earthquake shaking, which the building will receive. That is potential threat of occurrence of damaging earthquake. That is hazard. Then how we assess that? It quantifies into like physical expression, that is in the form of intensity of shaking. So we measure that in these three quantities or three parameters. One is acceleration, second is velocity, third is displacement. So acceleration, P ground acceleration, P ground velocity, P ground displacement. So these are the parameters we use in a design. And then there are some associated phenomena of earthquake, that is secondary effects also we can call: soil liquefaction, surface fault rupture, slope instability. But what is more important is we need to have a rational understanding of this hazard for assessment of, meaningful assessment of seismic risk. So this is in short hazard. Now if we look at, say, seismic hazard of the country. So as I said, zone 5 is this rearmost zone. And if we note clearly that megapolis, all the major cities are in, say, zone 3 and zone 4. And if we look at the area of like zones which are present in zone 3, zone 4, and zone 5, that means moderate to severe earthquake prone areas. So it accounts to be closely 56% of land belongs to this area, and 82% of population is living in that area. 82% of population is living in that area. That means what? If you pick 5 people, 4 out of 5 people are living in moderate to severe earthquake zones. And so what we have done was conducted a research in which hazard and exposure both are overlapped on each other. So you can see this is a population distribution map. In that each patch is one district. So you can see darker patches. So darker patches indicate higher densities, and clearly we can see that Indo-Gangetic plain. So here, where there are thick alluvium deposits and long period waves, if at all earthquake occurs at a distance, say 300 to 400 kilometers also, there is a possibility of long period waves. So why I'm talking in reference to tall building, this is significant. It's not that taken as lightly. And nearly 250 cities are there in this belt. 250 cities that are there in this Indo-Gangetic plain belt. And when we overlap this hazard and exposure both, then we've termed this as a housing threat factor map. In this one, every red patch needs to be focused. So we need to think about built environment in this red patch. So this map is not for scaring people, but for prioritizing earthquake mitigation activities. And when we look at, say, all major cities which are in this area, you can look at Delhi, okay, Mumbai, Calcutta, Chennai, Bangalore, Ahmedabad, Hyderabad. So many more cities are there, and they are located in these red zones. That means what? Threat is very high and we need to worry about it. Now coming to hazard estimation or hazard assessment. So what I'm going to discuss in this is two things. One is what are the hazard levels, And second is methods of estimation. So what is hazard assessment? What? It is actually evaluating the design parameters of earthquake ground motion. So that is called hazard assessment. And what are these design parameters? What are the parameters what we want, what we are interested in? Number one, amplitude of ground motion. Number two, duration of ground motion, duration of strong ground motion. And third one is frequency control. And then how do we do this one? There are two ways. One is deterministic approach. Second one is probabilistic approach. And then why we are doing this one? We are doing this one to understand the behavior of buildings when they are subjected to these ground motion parameters. Now let's briefly look into hazard assessment. So it is, say, probability with which a prescribed level of ground shaking, say that is 0.1 G, is exceeded over 50 years period. What is the probability? And second way of looking at it, it is what is the peak ground acceleration which is exceeded with confidence of 10% in 50 years. These are the two ways in which we can see. So our hazard map, if you look at our hazard map, it is based on likely intensities and that too past. So wherever earthquake has occurred, we have created a dot there with an intensity and we created a zone there, zonation. So it does not address how often that shaking is taking place. So for example, area A. So I take, say, somewhere in the foothills, say this yellow zone 3 area, say intensity 8 may occur once in 50 years. And I am taking another area, say deep south, somewhere here in Kerala, same intensity may occur once in 200 years. That means event may occur 8 intensity occur once in 50 years, 8 intensity event once in 200 it will occur. But our map is putting both in the same zone. So that means what? We are not considering probability, and this is very, very important. Okay. So now what are the, like, say, macro zones? So from 1962 onwards, so this is the first zonation map, second zonation map, third zonation map, and fourth zonation map. So all these zonation map had the same philosophy. Likely intensities and then epicenters are used for creating this zonation map. Now coming to this macro hazard. So what we have is a macro hazard map, and why we use this map? Where it is useful for, say, deterministic and probabilistic. There are two ways in which we can generate this map. Purpose of this is what? For designing normal structures. So to understand the confidence of safety and examine the adequacy of the design for next earthquake. So this is done over a very, very coarser grid, that is up to 300 to 100 kilometers range. This hazard macro zonation is done. And the second one is micro zonation. There are several, maybe around more than 20 projects have been done so far in the country of micro zonation map. Several cities. So Delhi and say Jabalpur, many cities micro zonation has been done. So effect on built environment and effect of built environment. So both are studied in that. And why it is used, the purpose of this mapping is for what? For disaster management and risk assessment, and also for land use planning, and also for building design. So this is one typical map. So the range of this is 10 kilometers up to half a kilometer. Then the next one, site specific. So this is for the site of interest. So better estimate of hazard than from seismic microzonation. Now purpose is what? It is for design of special structures and design of tall buildings. So that's why this topic has come. So for design of tall buildings, we need to do site-specific hazard assessment. And the details of this one, step-by-step details of this one, I want to cover in the second lecture. But presently, I'm focusing on 16700 provisions. So these details I'll explain in the next lecture. And its range is 100 meters up to 1 meter. That means 1 meter to 100 meters. So that we will know what will be the hazard, that is site-specific hazard in the project site, and to what level of ground shaking we need to design our structures. Now let's look at, say, earthquake behavior. So when these buildings, tall buildings especially, are subjected to an earthquake which has specific features in that ground motion, what is going to happen? So these two things we'll discuss, say with a reference to Nepal earthquake. So these twin Nepal earthquakes, they have occurred in 2015, one April 25th and second one May 12th. So while second earthquake was occurring, I experienced it, that I was present in Nepal itself. In Kathmandu, I was present. I experienced that. Yeah, you can see this is a bottom one is the cross section where you can see that all the geological how the geological setup and tectonic setup is there, and thick deposits are there. So because of which what we get is the long period waves. So Kathmandu Valley in Nepal is built on soft soil deposits, and then due to which long period waves dominate the earthquake ground shaking. So like this, it is evident from this ground shaking. Now what will happen if long period waves are there? What will happen? So let me just give you a glimpse of that. Can you see a small experiment here? Can you see the shaking?
Yes, Professor Pradeep.
Yeah, you can see that. So initially this is four towers kind of thing. So it's imagine that these are four structures. So four structures are there. Tall building is there, mid-rise building is there, and low-rise building is there. So when the ground shaking is very, very slow, that means what? Natural period, a period of the ground shaking is low. You will see tall building is getting affected. When we increase the frequency, so that means period is reduced. Now tall building is almost coming to rest, or intensity is very low, and then mid-rise buildings are getting affected. And then if we increase the frequency further, yeah, you can see low-rise buildings are getting affected. So all buildings are standing on the same ground, but so this is like school physics, we know that. So long period waves affect tall structures. You can see the example. So this is Darahara Square, that's tower collapsed. And then you can see another example. And then all the structures, say tall buildings, and then long boundary walls, which are matching with the frequency. So that is natural period is matching with the period of the ground motion, or predominant period of the ground motion. They got affected. So ground motion has actually three characteristics. One is amplitude, second one is duration of strong ground motion, and third one is the frequency content. So amplitude is simply you take the ground motion trace and then pick the maximum value, so that is peak ground acceleration. So here in this record it is 0.32 g, and then amplitude can be measured like say in three terms. One is peak ground acceleration, peak ground velocity, and peak ground displacement. So three things we can measure, and another one is horizontal amplitude and vertical amplitude too. And then duration of strong ground motion shaking. So duration of shaking actually influences the damage. Now sometimes what happens is high amplitude, short duration ground shaking may cause less damage compared to long duration but slightly lesser amplitude. So because of more stress reversal or more load reversals, damage gets accumulated, hysteresis energy gets accumulated, and that causes damage. So how do we account for it? It accounts for degradation of stiffness, and then in soil, that is increase in pore water pressure. Now how do we compute this one? So that energy curve, so time difference between 0.5% and 95%. So if we take that, that is the duration of strong ground motion shaking. Then the third important parameter is frequency content. So if we look at say this ground motion record, we take some portion of it and then do fast Fourier transform, and then second portion and third portion, we can see at different time instants what are the frequencies which are predominant in that ground shaking. So our whole time series we take, and then take the fast Fourier transform and check it. So we know what are the frequencies which are predominant in that. So that kind of buildings, the buildings which are matching with that predominant period will get affected during this one. So these three parameters are very important. And now these three parameters are influenced by other ground parameters, that is source, that is earthquake source itself, path and site. These are the three things. Now, if you look at the table, to cut short the story, I've condensed it. You can look at it. So duration increases if path increases, and then frequency reduces if path is more. So that means what? Long distance earthquake, even though they have lesser intensity, but period will affect tall buildings. So say tall buildings in Mumbai may get affected because of earthquake of say around 300-400 kilometers. So for example, tall buildings in Hyderabad will get affected if say earthquake repeats in Latur, or say earthquake occurs in Vijayawada area. So that kind of thing. So that's why tall buildings or high-rise buildings are treated to be special. Now coming to code recommendations. So what are the recommendations and what are the mandatory requirements? So I am taking reference from two codes. One is IS 16700 and IS 1893. Now what code says is there are four virtues. One is configuration, second is stiffness, third is strength, and a fourth one is ductility. So these are the four important things when we design. We have to ensure that our structure has all these four. Now let me come to some provisions. Now first, let's talk about say provisions related to form. So I'll discuss about height, slenderness ratio, plan aspect ratio, and openings in floor slab. Let's look at height. So what 16700 recommends is maximum height is 250 meters. Maximum height which can be designed using this code, 250 meters. And that too not all types of structural systems and not in all zones. So this table clearly shows that in zone 2 area, if the structural type is a structural wall plus frame tube, then up to 250 it is allowed. So, but if it is a moment frame structure, so what is allowed? What is allowed is only up to say 80 meters. 80 meters, that too in zone 2 area. So high seismic zones, maximum allowable height is 150 meters. And then moderate seismic zones, allowable height is 220 meters. And then low seismic zone, 250 meters. Then moment frame structure is not permitted in zone 4 and zone 5 areas. You can see here, not applicable, not applicable. So that means moment frame, I'll tell the reasons why it is not applicable. And then moment frame structure not permitted above 80 meters. So in zone 3, it is only 60 meters, and zone 2, up to 80 meters it is allowed. Now slenderness ratio. So again, maximum slenderness ratio allowed is 10. You can see. So 10, that to zone 2 and structural wall and frame tube, if it is that. Otherwise, if it is moment frame, zone 3 area, it is only 4, and zone 2 area, 5 slenderness ratio. So what are the issues if slenderness ratio is very high? So what happens is their structures, the buildings are susceptible for damage. So structural damage as well as non-structural damage. So how that will happen? It will happen because of the high drift ratio. So code is restricting drift up to 0.4% of story height. So if 0.4% of story height means drift is going beyond 0.4, so we have to restrict it up to 0.4, and accordingly we have to make the structural system. Select the structural system. So maximum damage is expected to be confined to first few stories in buildings with large slenderness ratio. So this is if we look at say basic mechanics also. So ends, if we take say tall building, it is a cantilevered structure. So fixed support is at the base. So what will happen is base will have a like Poisson's effect kind of thing. So whatever is the width of the structure up to that height, this Poisson's effect will be there. The damage will be concentrated there. So you can see that. So damage is attributed to Poisson's effect in lower section, and where end effects dominate. So at the lower section or lower portions of the tower. So that is the reason why slenderness ratio is limited. Then second one is say plan geometry. So a simple plan geometry is recommended in 16700. So either rectangular or elliptical. So these are the two. And why it is code is recommending these two geometries? Because members will participate efficiently in resisting lateral load, and without say if re-entrant corners are there, additional effects will be arising due to that. And then rigid diaphragm action. So if we take say rigid diaphragm action, like earthquake force is an induced force. Earthquake force is the induced force that is generated at the diaphragm level. So from diaphragm level, it will feed, diaphragm will feed to vertical resisting elements. So how it will feed the lateral force to vertical resisting element? In the proportion to the relative stiffness of lateral resisting elements. Now, if diaphragm itself is flexible, then the distribution will be in proportion to tributary areas of these frames. So that what will happen is, because of that, the frames or elements which are not designed to take lateral forces will suffer a lot. So force distribution is proportion to their relative stiffness. So if plan aspect ratio is less than 5, then this rigid diaphragm action can come in that. But if it is say long, that is more than 5, and if it has some openings also, then flexible diaphragm action takes place. So force is distributed in proportion to the tributary area in flexible floor diaphragms. So like structures, like in plan aspect ratio, say L-shaped buildings, we need to take that like wing or projected portion again, put the same condition. Okay, L-shaped building. Then re-entrant corners. So re-entrant corners, what 1890? This is the definition from 1893. So a building is said to have re-entrant corner if the projection is greater than 15% of the length in that direction, in that overall plan direction. So the building is said to have re-entrant corners. So what happens is poor earthquake performance will be there from that kind of structure, and stress concentration will take place at these junctions. Then other thing is this again accounts for flexible floor diaphragm. So excessive cutouts are there. So if excessive cutouts are there, the diaphragm action, rigid floor diaphragm action will slowly diminish because of excessive cutouts. So what code suggests is the area of openings, cutouts or openings should be less than 50%. Less than 50%, if at all it is there, it should be less than 50%. You can see this one. So if A0, that is area of the cutout, is more than 50%, then like flexible floor diaphragm action will take place. So that is not very much recommended. Then the next important thing is torsional irregularity. So quite often I've seen in projects, this is neglected. That means neglected, sometimes not taken care of very well. So what happens is a well-proportioned building will does not twist about its vertical axis. So what we want is building should do the translation x direction and y direction. So that is a good behavior of the building. Should not twist as it's the first mode. So stiffness distribution of vertical element should be in balanced according to the plan distribution, as in mass. Means mass distribution in plan. So as an example, you can see in x direction, along x direction, so k is the stiffness of one end and 3k is another end. In y direction, it is symmetric. So that means what? Center of mass and center of resistance, that is center of stiffness. So there is eccentricity here. In this case, what happens is building will twist in clockwise direction. So when building actually twists, what happens is beams will experience tension, or frames will experience tension at the top ends. And you can see this is eccentricity is there, or torsional irregularity is there in y direction, along y direction. In the first case, it is x direction irregularity, and second is y direction irregularity. But in both the cases, building will twist. So both combined here. So yeah. Now, how to say that whether building is torsionally irregular or not? So what these commercial programs do is apply 1 unit force at the center of mass and measure the displacement at both the ends. So delta minimum and delta maximum. So if delta maximum is 50% more than delta minimum, then it is torsionally irregular structure. So there are some other issues also because of this one. Okay, that I'll explain that. So if this delta max is more than 1.5 to say in 2 range, so what code suggests is ensure that the torsional mode is not coming as the first mode. So it is like x direction mode and y direction mode, and the theta mode, that is a torsional mode, should be the third one. And if the torsional irregularity, that is delta max, is 2 times of delta minimum, then you have to revise the configuration of that. So let me give one example. So in this one, so some provisions related to mainly mode shape and modal masses. So what are there in that? One is predominant torsional mode, then mass participation, diagonal mode, and maximum allowable natural period. So these are all clauses related to mode shape. So please focus on this one, predominant torsional mode. So what code suggests is natural period of fundamental torsional mode of vibration shall not exceed 0.9 times the smaller of the natural periods in each orthogonal direction. So if we say take x direction, y direction, whichever is the smaller, torsional mode, okay, should not be more than 0.9 times the smallest of these two, x direction and y direction, two translational directions. So just and as an example, so we have one of our student conducted this one. So you can see these are the mode shapes. So first mode, second mode, third mode, like that, up to 6 modes are given here. And then this is like period, according to period, these are what numbered. So first one itself is according to the participation, we can clearly say that first mode is torsional mode in this one. And the second one is like translation in the x direction, and third in this one is translation in y direction. That means T1 is the first mode. T1 is the first mode. And why torsional mode is coming as the first predominant mode? What is the cause of it? Let me show you that. Say in buildings where central core, shear walls are located in the central core, often this kind of like effect you will see. So in plan and so central core shear walls are located. So if that is the case, then we get say torsional mode as the first predominant mode. Now to avoid this one, what we need to do is, so keep say actually the torsion is coming due to core wall. Now if we like locate or if we put additional shear walls along the periphery, so this is just an experiment we did. You can put in different locations and check. So then how the periods are changing, how they are getting adjusted. You can see here the same thing. Torsion went to the third mode. That means third mode means torsional mode is lower. That means lesser than the translational mode, first translational mode in 2 orthogonal directions. So Tx is 1.72 and Ty1 is 1.59 and T theta is 1.44. So this is what code is recommending. And in addition to that, in this one, torsion is not predominant now. This kind of building is safe. Then other clause, what code says is, other clause, first 3 modes contribution shall not be less than 65% of mass participation. So again, the same problem, if we look at that, if we take out all the modes in each direction, say this is y1, this is y2, t1, t2, x1 and x2. If I separate this one, you can see this one. In x direction, along x direction, first 3 modes, along y direction, first 3 modes. So if we like combine the modal masses, which is coming to be 91%. And here combining all 3 modal masses in y direction, it is coming to be 82%. So like for all the analysis, we need to take total like modal mass contribution from all the modes is more than 90% of 90%. Up to that, we have to consider mode shapes, means modes in modal combination. But first three modes should contribute at least 65%. So this is the case. At least 65% they are contributing. But whereas in the earlier case, where central core wall is there, so there it was not contributing first three modes. Then other important clause is irregular modes of oscillation in two principal plan directions. So like how this is coming, stiffness of the beams, column bases and structural wall determine lateral stiffness of the building. Now a building is said to have lateral story irregularity in a principal plan direction if the first three modes does not contribute 65%, and this is second one I want to explain, like fundamental lateral natural period of building in two principal plan directions are closer to each other by 10%. So let me take the same example. Just 1 second. Yeah, so that is a diagonal mode. Now if you look at this one, say Tx and Ty. So here Ty is the like first mode in y direction. Tx is this Tx1 is the first mode in x direction. So first mode in y direction is 2.14, and then 90% of it is 2.16. So which is greater than like Tx1. So that means what, our mode should be lower than this one. Then next one is maximum allowable natural period. So what code says is the fundamental translational natural period in any of two horizontal directions shall not exceed 8 seconds. So that means what, the recommendations given in IS 16700 are up to this one, up to 8 seconds. So if it exceeds, suppose a building exceeds this one, what, so code is silent, maybe expert literature may be followed, and different structural systems may be adopted. Then the next set of clauses, what I'm going to discuss, that is provisions related to structural systems, shear lag, and clauses on analysis, drift, as well as secondary effects. Am I audible properly?
Yes,
Hello?
Professor, absolutely.
Yeah, thank you. So these are the structural systems which are recommended by IS 16700, moment frame building, moment frame plus structural wall systems, and structural wall, flat slab. There are some restrictions in each. So why we need to go towards the higher like a structural system, say multi-tube system up to. So frame walls, moment frame buildings up to multi-tube systems. So let me explain that. So let's look at, say, moment frame buildings. So what code says is the minimum 3 bays in each direction is required. Minimum 3 bays each direction, and then this moment frame buildings in seismic zone 3, they have to be designed as special moment frame buildings, and code is not allowing it up to, not allowing more than 60 meters in zone 3 and more than 80 meters in zone 2 areas. So why it is, let's look at that. So the members in the moment frame structure resist lateral load through axial forces, bending moment, and shear forces generated in beams and columns. Now, all beams have to be designed and columns have to be designed as under reinforced section, and there should be like predominant flexural behavior in beams and columns, that means should be facilitated. Now, how it is achieved? It is achieved only when we have long members. The members should be designed as long members. Now, in long members, this span to depth ratio becomes critical. Now, let's look at that. Say the ratio of flexural translational stiffness to pure translation, like shear translational stiffness. So that means what? Flexural stiffness to shear stiffness, that is termed as beta factor. So as you can see, this equation is like simply 3EI by L cube divided by GAS by L. So if we like remove, plug in the equations fully, that is I expand I and expand E and G, these will expand G and expand I, then what we get is this one. So it is actually dependent on dimensions of the member, that is L by D ratio and the Poisson's ratio. So this equation is for like if the structure is framing, that the member is framing only in one direction, framed only in one direction at one end, and then if say double curvature is there, that is framing at both the ends. So this is beta factor. Actually, this decides how the structure will behave. So predominantly shear behavior in the structure or predominantly bending behavior in the structure. So load transfer in this structure depends on like IB by IC ratio, IB by IC ratio. So if IB is small, that means building will behave like a cantilever. Building will behave like a cantilever, and if IB is large, it is shear behavior comes into picture. Now, what happens if it is cantilever? What happens if it is shear behavior? Like very important thing which we need to understand it. Like usual assumption is say under gravity loads. So we clearly see that point of counterpressures in column comes at the mid height. So that assumption is not valid always. So why? If say IC by IB is tending to infinity, IC by IB, that means what infinity means? It is a moment of inertia of column is very large compared to moment of inertia of B. So what happens is cantilever action dominate. When cantilever actions dominate, usually so lower floors experience higher bending moment value, especially lateral load resisting elements, say columns. And if shear behavior is there, shear behavior dominates. When it will dominate? If IC by IB tends to 0, that means what? Column like moment of inertia is like less, or B moment of inertia is very large. That means L by D ratio is in structures. So in like say like in tall building, usually wind is predominant. So when lateral load is applied either by wind or by earthquake, what happens is the columns in the leeward direction and windward direction, axial forces in the columns. Axial forces in the column, what happens is corner columns will have larger axial forces than interior columns. So in addition, like if the column spacing is large, the difference in column axial forces is large. So there will not be any uniform distribution. So let me show you that. So this effect, that shear lag effect, is attributed to what happens is inefficiency arising out of transverse deformation induced in beams due to relative deformation in frames. So let me show one example there. Yeah, so here the central core wall is there, and then so like peripheral columns are there, but they are very, very closely spaced. So two examples. So this is the data. So 40 meter by 40 meter square type building. So here this columns are at 8 meter spacing, here at 2 meter spacing, and then beam sizes are like exactly same, and wall thickness is same in both the cases. So here you can see the variation of axial forces in web panels here. Then traditional one, framed system and framed tube system. So framed tube system effect is less, framed tube system, and traditional system the shear lag effect is large. Here also you can see variation in axial force in flange panels. So these are web panels, these are flange panels. So in traditional structure, that is framed structure, so this is the variation, and framed structure, this is the variation. So framed tube is used with closely spaced columns to reduce the shear lag effect. Then the next one is lateral drift. So what are the provisions which IS code is proposing for lateral drift check or control? So what it says is, say when lateral forces are applied on building, maximum interstory elastic lateral drift ratio, that is delta max by H under working loads. So I'll define working loads. Now it should be limited to H by 500. That means 0.2%. 0.2%. It is limited to 0.2%. and in one story, in a single story, it is like relaxed up to 0.25%. So this is for wind loads. Okay, working loads unfactored, actually these are unfactored. And then earthquake load, that is factored earthquake load. Factored earthquake load is not load factor, it is the response reduction factor, that factored load here. So the drift is limited to 0.4% of story height. So what are working loads? Working loads are unfactored wind loads, and estimated using this drift limit is estimated using the like realistic section properties. So that is that. One second, let me tell you. That is table number 6 in IS 1670, tall building code. Then P delta effect. So this is also very important in structural analysis software. This is just a tick mark, but structural designer need to understand this the principle to appreciate the results in a better manner. So let's look at this one. So a tower or a structure where lateral force is V, and then like gravity load is P. So how do we calculate base moment? It's simple. So primary moment, that is V into S, is primary moment. Now, because of this primary moment, if say lateral deformation is large, so that is delta. So there are like 3 cases here. One is lateral deformation. So less lateral deformation and then less strain, okay, large strain, low strain, and then more lateral deformation and large strain, and less lateral deformation and less axial strain. So these are the cases. Now let's look at this MP, that is primary moment is V, that is V multiplied by H, V multiplied by H. But because of this V, if delta is the lateral deformation, so what will happen, an additional moment will get generated at the base because of this one, that is secondary moment, that is MS, secondary moment. So primary moment plus secondary moment is equal to total moment. MT is equal to VH plus P delta. So this is under the double curvature assumption. If it is a cantilever action is there, bending action is there, it is a single curvature. I'm not discussing that. Then we get that small delta, that I'm not discussing right now. So because in P delta, total moment is VH plus P delta. Now if we have to say apply an imaginary force that is V prime to create the same moment. So that means what? V prime into H is equal to total moment. V prime into H is equal to total moment, or V prime is equal to total moment divided by H. So if I do that, what I get is V prime is equal to total moment divided by H, means this H will disappear here. It is only V. P delta by H will remain. So this V delta, so V dash. So this V dash minus V is the effect due to P delta. This is P delta effect. This is the gap between these two forces. This is P delta effect. And additional deformation due to that is this delta prime minus delta. So this has to be accounted for in our analysis. Now if I divide this V prime by V, okay, as a ratio of V, then what I get is 1 plus P delta by VH. Actually, this is the stability factor which IS 16700 is prescribing. It should not be more than 0.2. So that means what? Secondary moment to primary moment, ratio of secondary moment to primary moment, it's termed as stability factor. It should not be more than 0.2. So if it is more, then we need to work on the structural system and bring it back, like it should be less than this value. Then next one is say in moment resisting frame and shear wall dual system. Two systems are there. What code suggests is when two systems are there, moment resisting frame should independently resist at least 25%. So let me give an example and show like how to look at this clause. So case 1, total lateral force shared by 3 moment resisting frame. You can see this example. So in this one, stiffness. So this K is used to just indicate stiffness. So 10 times K is the lateral stiffness of this red shear wall, these 3 red shear walls, red color shear walls. And then 35K is dark. Sorry, this red one is moment resisting frame, and then black one is a shear wall. Now in this case, you can see 30%. So total lateral force shared by 3 moment resisting frames is 30%, and 70% is by 2 shear walls. So what clause says is moment resisting frames should take at least 25%. So this case is fine. So we have to design shear walls for 70% of lateral load, design moment resisting frames for 30% of lateral load. But if the case is different, say now in this case, the shear walls are resisting 85% and moment resisting frames are resisting only 10 or 15%. So 3 moment resisting frames resisting 15%. So what do we need to do? So design moment resisting frames for 25%. Design moment resisting frame for at least 25% and go ahead with the 85% force on shear walls. No need to change that, it will get readjusted. So design moment resisting frames for 25% and remaining whatever is there, like design shear walls for 85%. So like percentage will slightly differ, but so design for that purpose. So this is dual system. So this is how we need to interpret the clause. Then yeah, so that response reduction factor to be used in such cases are tabulated in this one, not going into the details of that. And then there are some other provisions for irregularities, say out of plane offset, non-parallel frames, mass irregularity, stiffness irregularity. Let me touch upon few irregularity clauses. There are 5 plan irregularities defined in IS 1893 and 7 elevation irregularities. So if we look at that, one is torsion, as I discussed, reentrant corners also. Then openings in floor slabs. Openings in floor slabs will lead to flexible floor diaphragm, where like lateral load resisting elements will suffer damage if it is not rigid floor diaphragm action. Then out of plane offsets. This I will discuss in detail, and non-parallel frames. Okay. So like soft story, I'm just skipping these things. Yeah. So out of plane offsets. So out of plane offsets, you can look at this. Here, shear wall is provided in ground floor. You can see the dark, this one shear wall. Shear wall is provided in ground floor, but in upper floor, the shear wall is in other bay. So this is what is out of plane offset. So shear wall, once it is designed, it has to go to the ground in the same panel. Offset should not be there. So this is called in-plane discontinuity. So there is another irregularity which will come, that is out of plane discontinuity. So shear wall is in one panel and in upper floors it is in the other panel itself, not in plane also, it is out of plane. So this is out of plane discontinuity. So huge demand on columns in lower story. So that's why if it is discontinuous, then code puts the restriction on drift limits from that level, all the levels below that. Yeah, so what code says, lateral drift shall be less than 0.2 in the story having offset and all stories below that. So like code is restricting but allowing it. And then non-parallel frames. So if frames are non-parallel, so that is also not good for good seismic behavior, that is building vibrating in 2 principal plant directions properly. But if that is the case, then what code says is like in one direction, take full earthquake load and take 30% of the load from other direction and add into this one. So full earthquake load of one direction plus 30% earthquake load of another direction added in this one and applied. And again do the load combination. So that is penalty for non-parallel frames. Yeah, so this clause story stiffness in 1893, lower story stiffness should not be less than the upper floor stiffness. But whereas in 16, the tall building code, what code allows is lateral translational stiffness of any story shall not be less than 70% of the story above. So some kind of relaxation is there. So don't know what will happen in the next revision. Maybe it will go in alignment with the 1893 only. Yeah, am I audible properly? Hello?
Yes, Professor, carry on.
Yes.
Yeah, okay.
Yes.
Okay.
Please carry on.
Yeah, another like 7-8 minutes. Yeah, this one I'm skipping, soft story. The simple clauses only. A mass irregularity. One second, this we have discussed already, discontinuity. Yeah, now proposal for natural period of tall building. So what we have done was we wanted to check the adequacy. That means how good the empirical natural period expression given in 1893, does it hold good for tall buildings also? So for that, so we have done a study by testing, by checking the vibration, that is natural period of tall buildings in different cities, and then collected the data, did the regression analysis, and then proposed a new empirical expression for natural period of tall buildings. So if we look at this one, so the method is introduced for arriving at approximate natural period of buildings with basements, like step back buildings and buildings on slope. For all these things, what IS 1893's expression is, for bare frame, it is given as a 0.075 h raised to the power of 0.75, that is RC moment resting frame building, and steel composite, like RC steel composite moment resting frame building. And if structural walls are there, empirical expression is given in this manner. And then for all others, TA is 0.09 h by under root d. Now the question is whether this formula is adequate for tall buildings. So do we use the same formula for tall buildings? So let us look at that. So for that, what we did was evaluate the same for its suitability for high-rise buildings or tall buildings and propose new empirical expressions. So for that, we conducted ambient vibration tests using high performance micro tremor portable sensors, vibration sensors. So the principle used is force balanced accelerometer, and then frequency of the pendulum is up to about 200 hertz, and in the range of measurement, range of accuracy is 0.25 G plus or minus 0.25 G, plus to minus, and then it can measure accurately up to 5 into 10 power minus 3 gal. So gal is centimeter per second square acceleration unit, and the sampling rate is 100 hertz, that is 0.01 seconds. Samples are collected. So this is the picture of the instrument, and then the analyzer system program, and this is the network diagram of that, circuit diagram of that, and the test procedure. So what we did, installed or kept the vibration sensor after doing all the basic corrections of that, and alignment of the same in north, south, east, west direction. And then data is collected from around about say 15 minutes up to 45 minutes. So sensor is kept parallel to buildings major and minor dimensions. So like that. So this is a student named Pulkit Velani, who is presently doing PhD in Earthquake Engineering Research Center. So he's installing the sensor on the tall building, and then it is collected to LAN, and then 100 data points per second, and there is a storage device to collect the data. So I'm cutting short the story. What is the post processing after collecting the data? So this is how the first one, this is a raw data. So you can see long period waves are present in this one. Long period waves are present in this one. And then for that, we need to do baseline correction. So this, like something like a like noise kind of thing. Say, an equipment is vibrating at a longer distance, or say sea waves if you are near the shore. All those things will be captured in the building ambient vibration test. So once you do the baseline correction and do filtering, you get this kind of data. And after that, you do fast Fourier transform. So we have used the MATLAB software for doing that. And this is the Fourier amplitude spectrum. So clearly we can see peaks in this one. So these peaks account for natural period of the building. So you can see here, like this is the natural period. That's how you pick the natural period. So what we have done was we have measured several buildings. You can see here, say in Hyderabad, this building number we have given, say 45. So number of stories, n is equal to 17-story building, 22-story building, 25-story building in Mumbai, 31-story building in Mumbai, 37 floors building in Mumbai. So on this building, on the terrace, or maybe if terrace is not accessible, we have kept as far as possible. So student has done the survey for like a few days and then collected the data. And you can see this is the list of buildings surveyed, its height and plan dimensions are given here, longer dimension, shorter dimension, and the natural period, which is like real natural period of the buildings. Okay, so here list like 16-story building up to 42-story building. So that means approximately 120 meters height building from around 50 meters height building. So we have this data. Now, once we have the data, what we can do is regress the data. So does the regression analysis, did the regression analysis. A simple equation, linear equation is y is equal to mx plus c. But usually world over, natural periods are worked out using a power law. Y is equal to a, that is a coefficient, x, that is a parameter, to raise to the power n, sum. So you convert the same thing. So take log on both sides, you get this expression. And then we did the same thing. And we estimated the standard error and then coefficient of determination. And then what are the parameters to be used for empirical expression? We can use single variable for defining natural period, empirical expression of natural period, 2-variable formula where both the dimensions are used, and 3-variable formula where h, l, and d can be used. So single, 2, and 3. So what we found was single variable formula is more efficient. You can see this is a summary. RC, moment resting frame building, proposed formula. So what we are proposing is 0.032 h raised to the power of 0.75. With our proposed formula, standard error of estimate is 0.189. Whereas from compared to IS 1893-2016, error is more compared to this one. And this still, it can be further improved by doing testing on more and more buildings. And this is shear wall. So shear wall building. So what we found was buildings are more stiffer than what we are getting from the natural period expression. So up to 60-story and above 60-story. So what we can straight away take is for moment resting frame building, we can go with this formula 0.02 h raised to the power of 0.75. And for RC shear wall building, we can go with 0.01 h raised to the power of 1 point. So we have made like we are planning to give a recommendation to code committee and see how far they will adopt it. So, and then next, the last one, just 5 minutes, monitoring deformations in building. So earthquake shaking. So what code recommends is if building height is more than 150 meters, all such kind of buildings should be instrumented with triaxial accelerometers to capture like translational twisting behavior of the building during strong ground shaking. See, in other many countries which are technologically advanced than India, they have adopted this one. They are using this thing so that their database is rich, so that new improvements can be done in those empirical expressions. So this is a recommendation from IS code, that is 1670 tall building code. But what is in practice is not many buildings are practicing this one. Not many buildings are instrumented with this equipment. And wind oscillations also. If it is over 150 meters, then it should be instrumented to measure the wind speed. So in summary, I'm at the last slide. In summary, so what I have discussed is, so there is a prevailing hazard in the country. Many cities are, especially metro cities and the towns which are coming up. So they are aspiring for more and more tall buildings and high-rise structures. We cannot discount it because of the previous experiences. And then for that, what we have to do is follow the principles which are laid down in Bureau of Indian Standards. That is quite sufficient. So majority of problems will be able to solve if we follow Bureau of Indian Standard IS code, IS code provisions. And finally, what I wanted to re-emphasize is safety first. Whatever tall building we may construct, whatever fancy building we may construct, whatever we may do, safety is the first thing. So these are the one is hazard, second one is the past earthquake behavior of the building, and we need to understand the IS code provisions and what is the clause, and then implement those clause in our structural engineering practice. So I sincerely acknowledge or thank IS 30 for giving me this platform to present whatever I know on tall buildings. And then all my research students, sincere thanks to all my research students who have supplied the data, who have done the work for whatever examples I presented in this one. And not the least, some of the pictures I have taken from internet, that is a clip art. Then these are my contact details. And actually I have one YouTube channel by name Quakes and Codes, code provisions I am explaining in say less than 10-minute video for one clause in less than 10-minute video, and wherever possible example problem I am using. So if time permits, go and watch them. I think till now more than around 30 short videos are already there, but I'm planning to make videos on almost all the clauses related to earthquake engineering. So thank you very much, sir. I stop here. Tandon sir, over to you.
Yeah, thank you, Professor Pradeep. What an excellent presentation. And I like the way in which you made it so simple, and you combined both the code, that means 1893 and 16700, and interspersed them wherever relevant. That was something I think very, very interesting. And so I think that since the time is running out, let me take out questions which have been posted by the participants, which I think is the most important part of this the webinar. So Mr. Sushil Dhawan is asking, what is the difference between earthquake resilient and earthquake resistant? So
yes, sir. So that you have already answered. Yeah. So in a way, 1 second, sir, and let me.
I think they want to hear it from you.
Yes. So yeah, so resilience and resistant both are synonymous words. Actually, resilience is something broader than resistant. Resistant is only related to structures, earthquake, like earthquake resistance of a structure. So resilience means all other mechanisms come into picture. So like preparedness also comes into that, and how do we respond to that? All those things comes into that. So that is called resilience.
Okay, next question. What is government action in present to stop the construction of buildings who are not taking the structure, design, and earthquake effects in consideration?
Maybe I'm the wrong person to answer that. So if you want to do earthquake resistant design, maybe I can help. But what government is doing, we have to ask somebody from government only.
Yes, I think that's a very good
Actually,
answer.
sir, one more thing what I want to reiterate, this is not the platform to blame anyone. This is the platform to know what is right, how to do right. That's all.
Right. The next question is from Mr. Man Mehta. How can we develop fragility curves after performing non-linear analysis for any model building types?
Yes, sir. So these fragility curves have to be developed by some probabilistic methods. We need to have a suite of these vulnerability curves, and then there are fragility functions are available so that we can fit in that. Okay, sir, we can actually elaborate answer I can give offline.
Yes,
So,
I think,
yes.
Why don't you put it in your, what is that, quakes and whatever?
Codes. Yeah, sure.
Quakes
Sir,
and
sure.
codes.
So
discuss it
quakes
in
and
that.
codes, I'm mainly focusing on code clause, sir. Code
Okay.
clause. Yes.
Right.
Yeah.
The next question is, if an area is under zone 5 seismic hazard, but have not experienced strong earthquakes, what's the possibility that it will remain like that for 100 more years?
Sir, nobody can guarantee that in next 50 years, earthquake is not going to occur in that area. Nobody can guarantee that. Nobody. So earthquake is a low probability event, but high consequence event. So it is better to learn all the code provisions. That is enough.
Yes, I think buildings should be made to be earthquake resistant, irrespective of whether you had an earthquake there or not, depending on where you are. That's how you should proceed.
Something like, say, if a building is constructed in an area which practically no rainfall, so can we construct a porous slab? No. So like it's a parallel kind of thing. May not be a good example, but parallel.
Yeah. Another question, is it Poisson's effect affecting the lower zone of building, or Saint Venant's effect, since it is within the width zone? I think Saint Venant will come into the picture for torsion.
Yeah.
But
So this is actually it's a connected only. Actually, it's a connected only. Yeah.
So
Poisson effect at the ends, usually at the ends, it is up to the height. Sorry, up to the base height, up to the base width.
Yes, base width, I think. Correct. So next question is, sir, 0.004H drift check for which load combination? If I check the drift for response spectrum load combination, then it requires to match the spectral base shear with equivalent lateral load base shear. I don't know what he says, but I mean, I think the first part of the question is clear. You have to do the drift check under what load combination?
Sir, drift check is a gravity plus lateral load without load factors, sir. Unfactored loads. Unfactored loads are, we need to, drift check is with unfactored loads.
Yeah. And you take uncracked sections or cracked sections, or what is it?
Cracked sections.
Cracked sections.
So there are two columns in table number 6. Okay, unfactored loads are for lateral, means drift deformations, and factored loads are for what do you call it? Getting stress resultants for design. So these are the two things for capacity. For capacity, factored loads. For deformation, unfactored loads.
Yes. For deformation,
the cracked sections values are different for both the cases.
So I think that's the answer. When you're trying to do deformations, there is no response reduction factor to be applied, nothing. You just do the normal analysis and find out the deformation. Again, Mr. Sushil Dhawan. First question, how to take effect of vibrations due to wind for upper floors in tall buildings? Although, well, would you like to?
So we need to calculate the wind force, and if building height is more than 150 meters, it is better to do wind tunnel tests like site-specific studies for earthquake. So then we get a force from that. So wind is a force. So earthquake is the displacement applied at the base. So wind force has to be calculated and applied on the structure. And wind design is elastic design. Wind design is elastic design, and earthquake design is like nonlinear, that is inelastic. So that's why earthquake displacement is more than 0.4%, and wind restricts that lateral drift. Wind restricts lateral drift to 0.2% and 0.24% for single floor.
Anyway, for tall buildings, the code I think already mentions what is the maximum deflection that you can have, and also what is the acceleration from the point of view of comfort of the occupants. I mean, these are the two issues which you have to take into account. Next question is, please explain the rigid diaphragm action.
So rigid diaphragm action is something like, you can see my book. So this is a rigid floor diaphragm. When we apply force, say earthquake force is an inducible force which acts at the center of mass, and resistance. So from here, this load is, that force is fed to lateral load resisting elements. So usually it is good to design distribute lateral load, resistance in proportion to their relative stiffness. But what happens is, if the aspect ratio is very long, then building tend to bend in its own, that floor tend to bend in its own plane. So thereby central lateral load resisting elements will suffer more, like take more displacement compared to the edges. So that is the rigid floor diaphragm, rigid floor and flexible floor. In rigid floor, distribution is proportional to relative stiffness. In flexible floor, distribution is proportional to tributary area, and not advisable actually. Rigid floor diaphragm action is advisable.
Another question is, please explain the probabilistic and deterministic approach in the analysis of tall buildings.
So that one I will explain in the next lecture in detail. Next lecture, geotechnical aspects. In that I will explain, and some more time permits, some more classes also I will take. So there I am going to explain liquefaction potential assessment with an example, and then soil structure interaction analysis with example. If you do soil structure interaction, if you don't do soil structure interaction, what is the problem? If you don't do, what is the problem? If you do, what is the advantage? And then this site-specific hazard assessment also I'll explain. 3 things main.
Another question is, how do we determine the performance objective of a structure for a specific earthquake intensity? Except
It is a designer, sir. It is a designer. As a designer, we have to design it for what purpose our building is intended. Suppose say I am designing hospital building, so I decide my performance. And if it is a ordinary residential building, I decide. I means designer, structural engineer will decide that. If it is a secretariat building, government office, maybe if it is a nuclear power plant, all these things are decided by the designer or for an intended purpose.
Is there any parameters specifying the allowable acceleration velocity at values?
This zone factor is that one only. Zone factor, whatever is given, is for maximum earthquake, and that is double of the design earthquake. So that's why it is used as Z/2. And this part also I will elaborate in the next lecture.
Okay. So how do we propose time period equations compare with those in the international codes like ASC 710? I think what he's worried about is this what you mentioned as the empirical formulation about that 0.9 and by under root.
Yes, yes. So we need to do a lot of experiments, and as I mentioned, I also call what code is recommending. All the tall buildings over 150 meters height, if they are instrumented, we will get the real data, ambient vibration data as well as real data. For ambient vibration data, we need a high sensitivity equipment so that we collect ambient vibration data. And real data, when strong ground motion, that means when a real earthquake occurs, what is the natural period with which building was vibrating. So those 2 things, it will make our database rich, and then we can propose or we can improve our code, empirical expression.
I think before we end, there are a couple of questions by Mr. Amit Patil, which I think needs to be addressed. As per amendment number 2 of IS 1893, first 3 modes, 65% participation provision is not applicable to building with large podium in lower story. Can you elaborate it?
Yes, sir. So buildings with large podium, it will have a lot of missing mass. So that is the reason why it is there. But still, maybe amendment will come. Amendment means we need to study that properly and then give a real behavior. So if possible, I request the consultant to have a separate discussion so that we see whatever building they are designing, what value they are getting. So missing mass correction is an important thing there.
Yes.
So especially podium, whether it is it has retaining walls on the side, or it is like completely rigid at its base. These are the factors which we need to take into consideration.
Yeah, I think let's take the last question before we close. As per table 9 of 1893, in flat slab structural wall system, the wall shall resist 100% and perimeter 25%. So is it total to 125%? As per
Yes.
table 9 of 1893 in flat slab construction.
Yes. So these that shear walls are to be designed to take 100%, and at least 25% is by the perimeter frames, perimeter walls. Sorry, perimeter walls. Yes,
Yes.
it is more.
Theoretically, you're designing for more force, but
Yes.
you must remember that with shear wall buildings, they will automatically deflect the floors, the frames in the direction in which they are moving. So they must be designed for something, and they have said that it should be 25% in the code. Okay.
And there are restrictions when we use the shear wall type of building on response reduction factor also. Maybe I'll discuss in the next lecture. Okay, today time is not there, but response reduction factor also there are restrictions. Yes.
Yes. So can I now request, I think our president, Mr. Manoj Mittal is here. If he wants to say a few words before we actually close.
Okay, thank you, Tender Saab. Just I want to congratulate Dr. Pradeep, R. Pradeep Kumar. It was a very informative and excellent lecture. He actually discussed all the major clauses of 16700 tall building code. And this presentation was like from a teacher to student, like it was really very interesting and very nice to listen to this. And also we came to know some of your research which you have done, some of the studies which you have done. I'm sure the findings will be quite useful and maybe included in the BIS course. I hope so. So I'm really very happy that we are having this kind of lecture. And further, I'm happy that you are not an outsider to us. You are part of our ISTT family, and you are also Vice President South. So it is really very interesting and very nice and very satisfying to have this kind of lecture on our platform. And we are really looking forward to your other 3 lectures in this series. And I'm sure they will be equally interesting and useful. I just want to thank everyone. Tanda Saab, as usual, you have conducted this as a moderator. You have done a fantastic job. You always do that actually, either as a speaker, as a moderator, or as a panelist. You always do fantastic job. Same thing you have done today also. Very nicely conducted. And I also thank all the participants for joining, and I also want to inform all the participants that we are also starting a refresher course on structural retrofitting and rehabilitation. It will be a very interesting course and very useful course, and all senior experts in this field will be taking the lectures. So details must have gone to you, and I request everyone to register it and also propagate this to other colleagues so that they can take advantage of this. And also I will request all participants who are not the member of ISTT to become the member of ISTT, to join it and get associated with various activities. And if you will join, I'm sure ISTT will be more strengthened and we will do much more work. So becoming member is not very difficult. Just go to the website, download the form, Just check your eligibility criteria, send the fill-up form, and then rest of the things we will do. Okay. So that's all. Vishalakshi, if you want to say something, just say something.
Yeah. Thank you, Manoj. Yeah, I just want to thank Pradeep for a wonderful lecture. It's always pleasure to hear from him. He always put the difficult things in a simple way. That's the beauty of a teacher. Okay, thank you, Pradeep. We are glad that you are organizing 4 lecture series on disaster resilient India. And thank you so much.
Yeah, and Dr. Pradeep, you can also inform the audience regarding your lecture, which you have proposed in as a Vice President South.
Yeah. So, as a Vice President South in this region, we are proposing monthly one lecture. The first lecture is on 27th by Professor Arun Menon of IIT Madras on heritage structure. So that is assessment retrofitting of heritage structure. I request all the participants to join that and make it a grand success. So already, like, many people have registered, but those who have not registered, please register in that. That is one thing. And second, one more thing I wanted to add is, there is a journal, which is quarterly journal, which is released by IA Study. In that, there is a series called Know Your Codes. So every edition, we are discussing one code in detail with example problems, comparison with other international codes, so that we can easily know what are our strengths and weaknesses in terms of codes. So it's not to criticize anybody or any organization. We need to learn good things from everywhere. So whatever good things are there, we have to learn and continue to do our practice. So,
and further, this quarterly journal that is called SED, Structural Engineering Digest, Dr. Pradeep is the chief editor of that. And the next issue which will be coming up is on the theme of structural health monitoring of the structures. Professor Suresh Bhalla of IIT Delhi is the guest editor of that issue. And I will request all the participants, if they want to contribute an article on this theme, which they think they have done some case study, or they have done some work on this, or they have some research work to show, they can contribute a paper. They can contact IS Secretariat, Vishalakshi, or Dr. Pradeep, or anyone in IS Governing Council, and you can contribute that article also.
So you see how the president is so generous. He has said that all participants. So whether you are a member of IS Shakti or not,
yes,
you are welcome to send a paper on any subject that you feel like. It has to be of structural engineering, because that's the subject that it has to relate to. But you're most welcome, and you will, if you join the IA Shakti as a member or a fellow, you will see that the generosity doesn't stop only there. The generosity, you'll get many more things if you do become a member. So suggestion is that please become a member if you are not a member, and get other people to do the same. Thank you. Okay, then I think it remains only for me to thank Professor Pradeep for a wonderful lecture, and our president, Mr. Manoj Mittal, and of course, Professor Vishalakshi, our honorary secretary, for being present both and giving their words of advice. With that, I think we have come to the end of this webinar. I'm sorry, there's one thing I completely forgot to say. This entire series has been, the concept has been made only by Professor Pradeep, and so he gets the full credit for this entire series that you are going to be witness to. So with the first lecture itself, you must have got an idea as to how exciting this whole thing is. Okay, thank you very much.
Thank you, that, thank you.
We will close.
Thank you, Vishalakshi.
Thank you, everyone.
Take care. Bye.